Hello and welcome to our annual Thanksgiving review. This is third in a series, a third annual Thanksgiving calculus review. And this year we are featuring Calculus 2 and Ugly Christmas Sweater. It's a special edition. About 700 showed up. Thank you for this great turnout. Yeah, thank you. So, I guess Thanksgiving Xmas sweater review. That's good enough.
Yeah, it does look like a formula. Perfect.
It looks like a formula from Calc. Yeah, yes, we do have a domain X and then excellent.
So the first offering is the Larson book, 8.2, problems 33 and 35.
Yes. We are talking about, we are opening this session with series questions. Larson book section 8.2, problem 33, not 3.3, 33. And it says summation from 2 to infinity 1 over n squared minus 1, which is telescoping series because we can do a lot of work using partial fraction decomposition once we factor this into n minus 1, n plus 1, and then running partial fraction decomposition. So we will have a over n minus or n plus 1 plus b over n minus 1, which gives us 1 over n minus 1 n plus 1. And now we are going to go with the equation an minus a plus bn plus b equals to 1. A plus b n minus a plus b equals to 0n plus 1. We equal the coefficients. I know that I'm not supposed to use red and green, but oh wait, it's not Christmas. It's a sweater, so I can use the red and let's use red and blue on white. It's good. So we have a plus b is equal to 0, and negative a plus b is equal to 1. If we are to add these two equations, we will get 2b is equal to 1 from where b is equal to 1/2, and then immediately a is negative 1/2. Negative is associated with n plus 1. Okay. Yes.
Why?
Because.
Oh, because it's over. Okay.
Right. So we are going to have summation of negative 1/2 divided by n plus 1 plus positive 1/2 divided by n minus 1. But I'm going to swap this and make it into 1 over 2n minus 2 minus 1 over 2n plus 2. So what I've done here is I distributed the half, right, which distributes in denominator. And then I swap the order of the two, so I have the positive term first and then the negative. It goes from 2 to infinity.
Did you have this taken out the 1/2 all the way in the sun? Or do you have...
There is actually much better idea, which means I'm going to erase all of this. Take 1/2 in front, common factor, 2 to infinity, and then I will have 1 over n minus 1 minus 1 over n plus 1. I still swap the two terms.
Where it was a plus b parentheses n minus, is that a 0 n plus 1?
Yes, 0 n plus 1.
See if I can keep circling back to the same thing. I think it's part of what's confusing.
What chapter in this book is this?
This would be telescope 8.3 in our textbook. This is telescoping series. They are not emphasized in our textbook as a separate test. It is emphasized in Larson book. So in our book, I believe there is 1 or 2 exercises given as a, oh, by the way.
They're not clear.
Yeah.
But I didn't find the Larson ones clear either. They jumped all over the place.
Yeah.
Okay.
Well, this is why you have me.
This is why we have it.
All right. To make a big deal out of telescoping series, we have 1/2, and now we're going to open the big bracket because 1/2 has to multiply everything that we do with these terms now. And we are going to now start telescoping. So open parenthesis and use 2 first. So which is going to be 1 because 2 minus 1 is 1.
So we're starting with 2 to make 1.
Yes. So 1 minus 1/3. And then plus the next term is 3, so it's going to be 1/2 minus 1/4. And then plus, then we are using 4, which is 1/3 minus 1/5. So 2, 3, 4, 5. So 1/4 minus 1/6 plus dot 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 will be going forever. And then if we look at the tail end, we will copy the last as 1 over k minus 1 minus 1 over k plus 1. It's the same. It looks the same as the series.
How do you know to do that? That's my question.
Because what we are doing in this case is we are making this series to be a finite series.
Right.
So the last value we are going to compute it at is k, n equals k. So if I am computing it at n equals k, then every n gets replaced by k, and that's why it looks the same, just n replaced by k.
Well, why do we do K?
Because we want to remember that the finite series is always easy to compute because it has the finite number of terms. So we just add and subtract all the terms that we have. And then what we are doing is we are going to that k, which is arbitrary number, and then we are going to send that k to infinity in the limit. So technically cheat, right?
Okay. All right.
So now we are supposed to subtract 1 from each k. So it's going to be 1 over k minus 2 minus 1 over just k.
We're subtracting 1 from each?
Because, yes, it is a previous term.
Okay.
So now we are still subtracting 1 from each. We are always going to subtract 1 from each, going back now. So we have k minus 3, and over here 1 over k minus 2 minus 1 over k minus 4, and so on. And now we're going to start canceling, and then we're going to take the limit of, so 1/2.
Can you stop for a moment? Because this is where I start to get really confused. All right, you're going to post this evening too?
Yes.
Okay. All right, I'm going to watch you carefully and say right.
So now what we are going to do is we are going to cancel positive 1/3 and the negative 1/3 because they add to 0. Then I also see there is a quarter and a quarter. The next term over here would be 1/5, which would cancel this one. with this one. And then the next parenthesis would have 1 over 6, which would cancel this one and this one. And you can see that all of them cancel. The ones that survive are 1 plus 1/2. Those are the ones that survive.
For the ones that actually have numbers in them.
Yes. Now looking at the back, you have the same thing happening. And I mean, by the rule of thumb, it's symmetrical. You see how when you're looking from the front, first and third survive. The same thing will happen from the back. The last one and then the third from the last would survive as well. And everything else would cancel with.
See, this is basically, you're making lots of assumptions with this.
No, you don't. Actually, if you work out enough of these examples and write enough terms, there are no assumptions.
Well, assumptions is probably the wrong word. One is knowing that certain things are going on and canceling based on that,
Yes.
even though it's not written.
Well, if I am to write more terms, it would definitely be clear that they're all canceling.
But the 1/5 and the 1/6 and then the 1 over k minus 1 to do 2.
I am going to, that's true, and I'm going to just make the following observation. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, 1 over 8. You see? So they all exist one by one, right?
Right.
So definitely the two next parentheses would have 1 over 5 and 1 over 6, which cancel this one and this one, and so on.
Okay.
So that's why it's important to write enough terms. And as soon as you start seeing the patterns, it gets to be easier in terms of you can be lazier and not write as many terms. As soon as you pick up that, you know, the pattern is 1 over 1, 1/2, 1/3, 1/4, 1/5, 1/6. And then when you see that the others is off by 2, 3, 4, 5, 6, again, the second one, you see the 1/3 and then negative 1/4, negative 1/5, negative 1/6, negative 1/7, negative 1/8. All of them will have their positive counterparts, which we call additive inverses.
Right.
They all cancel. So the only two that do not have their inverses would be 1 1/2, and those are the ones that survive here at the end.
Okay.
And from the tail end, we have the same situation, except we are going to add 0, so we have a minus limit k goes to infinity, right? Because series is supposed to go to infinity. And yes.
Question: how many do you generally say that we should go up to when we're going over 6, to 6 terms, 7 terms?
It depends on the problem. In certain problems where these values are by 1 apart, you only need 3 terms, and then you will see. Generally, you can actually keep writing these terms until you see that one entire parenthesis will cancel. So you see in the first 2 parentheses, 1 term remains, and the third parenthesis, the first parenthesis, were both canceled. After that, every time both will cancel. So you can keep writing these terms until you spot that there is a parenthesis that has both of them canceled, that you already see they're canceling, and then you can stop. And you can just, from the tail end, write as many. So I was supposed to do 1 more term, but I haven't. Oops. Right? Both of these in the limit at the end go to 0 because one.
First of all, that's a negative. That 1 over k is a negative.
Yes, there is a negative in front,
Okay.
so I pull the negative in front of the limit.
You pull the negative in front of the limit. Okay.
Yes, which will distribute and make both 1 over k and 1 over k plus 1 negative.
So we know that this is what we're supposed to do. There's 1/2 of this that's just regular numbers, and then there's 1/2 of this that's on the other side of the limit.
Yes, which is the k terms, yes.
Okay, all right.
And now this is 3/2, 3/4. So the series 1 over n squared minus 1 from 2 to infinity adds to 3/4 when you add all of the infinity of the terms it has. It adds to 3/4, clearly converges to 3/4. Please remember that geometric series and telescoping series are the only two series that we know what the sum is because we have the formula or a procedure to compute. Others we don't. We just know convergence or divergence. Yes?
So the telescoping series, that's the only way to do the sum there? Okay. And the geometric series, it has its own little formula?
Yes.
A over 1 minus r?
Perfect. A over 1 minus r. Geometric series is scary because it has to start at 0, so we have to make sure that all of the formula looks identical, right? Yes?
Is both the limit always go to 0, or?
No. I can have a square root of k plus 1 minus square root of k. It will still be telescoping series, but in the tail end you will have infinity, and it would not go to 0. So that one would actually diverge. It depends on how the problem looks like.
So something, in the case of things like infinity, when infinity is involved, infinity plus any given number like 1 will be infinity no matter what.
Yes.
And therefore we have 1 over infinity, which goes to 0.
Yes.
Okay. All right. Cool.
Of course.
Can you go over changing the bottom part?
Yes, we have one more problem, then we'll jump to, well, then we'll jump to geometric series and change the. Oh, thank you.
This is disgusting. I don't know if you want
Problem 35 from the same Larson book on same page, same section, same everything, and it's going to be the same problem.
Well, but, in this case, if they don't feel, if somebody feels something's more important, is now that I get what you're doing, you don't have to go with 35 if you don't feel like it.
Let me just get the feel in the class. Would you guys like to do this one on your own real quick, and then?
I'll do it on my own.
Yeah, do on your own. So you get 2 seconds while I go get the water. So you get 18 seconds now. No pressure.
two fractions that add to the x. And then once you get that, you have to telescope the series. If that's the formula for it. How do you get negative?
Do you get a plus b is equal to 0?
No.
So a is equal to 8 plus negative 8 is equal to 0.
What about
And then 2a is 2 times 8 equals 16.
which is okay. I thought for some reason it was 2a plus b equals 0.
No, it's 2a
Yeah.
plus b is equal to 8.
I know, I have that written down.
Okay.
I had that written down, I don't know why. Is that math?
No, it's not this thing.
I don't know.
IBM. You know what IBM is? It's one of the oldest computers.
Do you know what IBM stands for?
I used to.
I believe it's.
No, it does not stand for
I think it was International Business Machine.
I've heard that before. You plug in 0 first, right?
No,
Plug in
it's
one
only one.
first.
Yeah.
The first value you get is 4. How? What was
Oh, you told me 8 out? You can do that? Yeah.
Call the AI.
Oh, if you do that, you should it. This is what happens when I post you that other video. Is anyone watching the video?
0 are watching the stream, which means we'll keep the stream on.
Yeah, please do keep this in mind, because I'd like to look at this when I get home. Not when I get home, I should say, on Friday. I would like to look at it so I can follow everything. I have found that extremely helpful, the stuff I miss.
Yes. So a plus b is 0, and 2a plus b is not 1, it's 8. It's 8. So I will subtract these two equations. 2a minus a is a, b's are gone, so a is equal to 8, and b is equal to negative 8. That's infinity.
Oh, that's where I came nicely.
And now we are going to write the series as 8 over n plus 1 minus 8 over n plus 2, and we are going to kick the 8 outside because we can, 1 over n plus 1 minus 1 over n plus 2. And this is the part where they are 1 apart. So what I'm going to do is I'm going to, so here's mathematical correct notation. I'm going to find the limit as k goes to infinity for the series 1 to k of 1 over k plus 1 minus 1 over k plus 2.
Why, I'm sorry, I'm missing why you can do this instead of doing the other one.
Well, all I did is, oh, and there's 8 there. All I did is I replaced infinity with k, so I made it a finite series, and then I send that k to infinity.
Well, why didn't you do that with the other one?
Well, that's what I did. I just didn't write the step. So this step explains in notation.
Oh, this is before you go into the.
Yeah, into fractions.
Okay. All right, that's
So now
what I'm getting.
we compute the first term, so we have 8, and then this one, and now I say 1, so that's a 1/2 minus 1/3. And then plus 1/3 minus 1/4. Plus 1/4 minus 1/5. Plus 1/5 minus 1/6. So let's see. This will cancel. Oh, this is actually too much, but that's okay. Tail end, copy 1 over k plus 1 minus 1 over k plus 2. Plus the term before will take away 1 of the k, so 1 over k plus 1, 1 over k.
Can you explain that part you just did there? Right there.
I'm taking away just minus 1, so
I see.
this
Okay.
term,
All right.
right, the last one is the same as the series, and then minus 1 on each.
All right.
K minus 1, k minus 1, 1 over k minus 2. And now we start canceling. 1/3 and 1/4. And this is what I know. As soon as you see that second parenthesis, both canceled. I don't actually have to go further, but we know all of these will cancel.
As soon as you saw what? The second parenthesis?
It looked like this when I said it.
In the second term, it already started canceling.
See, this one had both terms cancel. That means that after that one, everything else cancels.
Oh, okay. Good. That would be the things I can.
And then these ones, and then these ones. This one will cancel
And
here.
that's always the case. Once one term cancels out, all the rest of it.
After that, yes. That's the one you can always bank on. So now we have limit k goes to infinity, 8 times the limit. 1/2 minus 1 over k plus 2. This guy goes to 0. So it's 4. Right, 8 divided by 2 is 4. And that takes care of the problem. The next question is on geometric series. Yes?
What would be like your absolutely final answer? Like it would be since convergent.
It converges to 4. So series converges to 4.
Okay. No fancy.
By telescoping series, yes.
No fancy.
I'm sorry, but no fancy stuff.
If you're taking the limit before you're doing all of these fractions, why do you have to do it again?
He was just notating.
Oh,
the way-
oh, you're right. I forgot to write the limit over here. Thank you. I forgot to write that limit.
I think he was talking about above. That he was just, I get confused too. He was just showing us his future notation, where he was going to go with it, right?
Well, what I did is I replaced, let me just write that I replaced this with that. So instead of having infinity here, I have infinity there for k. Nice! Just like the integral for Riemann sums. Very good. Exactly.
You're just demonstrating up there what's gonna happen below, basically, right?
Yes.
Okay.
Well, it's not demonstrating, it is actually, this is the step where I say, I don't know how to, I don't know. I don't have time because eventually I'll be old and die. I don't have time to add all of the infinity of the terms. So what I'm going to do instead is I'm going to add a finite amount of terms. So this is actually a genuine step in a problem where I am changing the infinite series into a finite series. And a finite series I can add term by term. But to battle the infinity, To battle the infinity, I am going to take the that k and send it to infinity.
And then
You want to say simulate infinity?
And then you follow by doing exactly that.
Yes. And then all of this over here is the expansion of this idea. So this is how it looks like when it's written out term by term. And then we see the pattern, we see cancellation, and we see exactly what survives, which are these.
Right, but now I finally understand it, but it's not getting it.
Perfect. Yay.
So why do you never have a series that goes to like negative?
Counting numbers count up to positive infinity, and all the sequences are ordered to are ordered over the set of natural numbers n. Set of natural numbers actually starts at 1, the way you count. If I'm to count 700 students who showed up today, it would be 1, 2, 3. I wouldn't go and start in a corner where there's no one and say 0, 1, 2, 3. Or I wouldn't definitely count you as -1, -2, that you get you upset, right? Because you're -1. So counting numbers, which are the numbers which order the set of sequences, start with n, 1 equal 1, 2, 3, 4, 5. So that will go to positive infinity. And then the series is the sum of the sequence, which means it's just using everything from the sequence, which is, again, the counter, which is 1, 2, 3 to positive infinity. That's why there is no negative infinity involved.
Put it more succinctly, because he said, sort of like memorizing everything, this is chapter about memorizing.
The next problem is shifting the counter in geometric series. So here,
The one you book for that?
yes, geometric series look like this: AR to the K arc, where K starts at 0, goes to infinity, and it's convergent for R's less than, well, R's that are in between -1 and, so -1 less than R, less than 1, and divergent otherwise, which means that if you have 1 or -1 or 7, right, so it's outside of that region. And then if it's convergent, then sum is equal to A over 1 minus R. So this is the definition for geometric series. And now we can do the problem. The problem would say they have a lot of different geometric series. Here's a cute one, but this I'm going to modify it, so it's not exactly like it's written in the book, so I'm not going to give a number for it. It says summation of 4 over 2 to the n from 2 to infinity. So I'm immediately going to circle the 2 and put the frown next to it, because, right, we see that it should be 0. This is something that you must memorize for geometric series. It has to start at 0. In our case, it doesn't. It starts at 2. So let's do some work first. In terms of algebra, I'm going to write this as 4 over 1/2 to the n.
When can
Maybe I can put an extra step. Yes.
when can you ignore the Precalculus substitute for geometry?
Only if you are looking for convergence or divergence. But if you are looking for the sum, then you must shift. So we know, as you can see here, that convergence or divergence does not depend on counter at all. It depends only on the value of r. So if I only need to claim converge or diverge, I don't have to worry about the counter. But if I want to find the sum, yeah, then we have to shift, because the formula works only if counter starts at 0. So our counter starts at 2 everywhere, which is the issue. Now convergence here is not an issue at all, because we see that r is equal to 1/2. So since r equals 1/2 less than 1, we see convergence by geometric test. So convergence is not an issue even for a second. But what is the sum?
How can you decide whether it's convergent or not if you don't shift the counter first? Because once the
R can never change.
oh, it doesn't.
It changes the value of A. So if you don't shift the counter, you would have wrong A, and the sum will be wrong when you compute it. So the counter, you will see now when we do all of these calculations, once we shift the counter, you will still have the same R. The A would be different, and clearly A, right in the formula, A over 1 minus R. R staying the same, A being different, will give a different value.
So what you're saying is, once you change the counter,
Value of A will change.
A changes, but R does not.
Yes.
I think that's what I was getting at.
So let's take a look. Summation 2 to infinity, well, this is now n equals 2, of 4 1/2 to the n. So what am I going to do? I'm going to subtract 2 on both sides on the counter, because I want to have it equal to 0, which gives me that the counter now is n minus 2 equals to 0, which is exactly what I want. But it's just annoying that it's n minus 2 now. So I have this, but I don't like n minus 2, so I'm going to call that, let's say, k. Or I can pick any other value, m or whatever. So let's say we'll call that k. So if I call that k, then I will have k equals to 0, which is better. K equals to 0. Now that looks like a formula. But now the problem is that you can't put 1/2 to the n. You also have to change that into k, because you used the substitution to change n in the counter into k. Now you have to change the other n into k, which would clearly be k plus 2.
Why is it clear what you're supposed to
Because n minus 2 is k, n is k plus 2 when 2 goes to the other side, right?
Okay, that's why I really.
So it's like a back substitution from
Okay,
for integrals.
yeah, all right, now I get it.
So now I have summation k goes from 0 to infinity. That's awesome. 4 times 1/2 to the k times 1/2 squared, because I peel off those plus 2 on k's.
But when you're saying plus 2, you peel off the plus 2, you're separating out the k and the 2?
Yes,
The k plus 2 is 2 different terms, and you multiply them.
yes, that's the algebra formula of.
That's,
So now this is 1/4. 1/4 times 4 is 1. So I hope you see that this is just 1/2 to the k now. And the value for A is 1, value for R stayed unchanged, which is a half. And we can compute the sum as 1 over 1 minus a half, which is 2.
How did you get rid of the 1/2 squared?
1/2 squared is a quarter. 4 times quarter. 4 quarters is $1. Yep, they cancel. So I hope that this was clear from this example that all of our R remains the same and A, value of A changes from 4 to 1 because of the shift in the counter. And we have A equals 1, R equals a half, plug everything in the formula A over 1 minus R, and the value is 2. People out of 700 clients. It's right proportion. It's exactly right proportion.
When you're ready, I have 2 more questions. Nobody else has questions. I don't want to be a pig. Bless you.
You can also type in software call.
So we can do this, we can put it in software. So
Yeah.
you just copy it.
You will not be typing the steps. I have no clue whether useful this is.
Because per your instructions, you want to give the final math so we can tell the story around it.
Any other questions? Or are we going home?
No, I got 2 questions and nobody else. I don't want to be a pig, yeah.
We are open to chapter 6, 7, 8, and 9.
I have 2 problems here from homework. One on each side.
Right.
And I think that's what easy is 28, 24, so I think I understand it from the side.
Okay.
What is P series is
They're busy doing chemistry right now.
I'm sorry?
They're busy doing chemistry.
Who?
Yeah.
They said P series.
Oh, I thought you said something else. I thought you were doing chemistry.
Can we do chemistry?
They were doing chemistry.
General chemistry is fine, but organic chemistry I don't speak. I don't speak organic chemistry. General chemistry is not a problem at all. They give you units. So you have the units, you just put the formula back together.
See my class prep, we're on a bunch of chemistry problems.
That's how you spend time. The next problem is from, I believe, 8.4
Yes.
from our textbook, and it is problem number 9. And we are going to take a look at the series that starts at 0, goes to infinity, k over 2k plus 1. Now, we learned 10 tests. And I gave you the sheet which contains all 10 tests. Hopefully you didn't lose it. If you did, copy it from someone. Or apply for a new one. It's $100 per page now for negligence. On those 10 tests, the first test that is listed is called the nth term test, and we call it divergence test in our textbook. That one says that if the sequence within the series is not 0 in a limit, then the series is divergent. So I will write this one more time. This is a series of AN. This is the general shape. Let's go from 0 to infinity or any number to infinity. This is the general shape for series. So the entire thing is called series. But this AN part is a sequence. So when I say sequence within the series, that means the AN part, when you take the sum off, because the sum is the one that replaces commas into pluses, right? Changes commas into pluses. So AN is the sequence. And then series is the sum of the sequence. So now this piece is a sequence. This is your AK. And when you take the limit of this AK in this problem, which is k over 2k plus 1, as k goes to infinity, the limit is 1/2, which is different than 0, which means divergence by divergence test, or as the Larson calls it, the nth term test. So that test is to be tried first on every single series you see. You immediately look at the sequence within the series. And if it's not going to 0, the series is divergent immediately. This is the same idea like for integration when you went and say, is this a basic integral? Is it a U sub? Right? So this is that first thing you try. Right? This is the first thing you try. Divergence test. If it is, if the sequence in the limit goes to anything but 0, series is divergent and you are done immediately. So on your exam, at least one problem will do that. So if I hand you the exam with 10 series, your first response to that should be, let me run all 10 series visually against the limit procedure here for the sequence, and well, just a series, right? And then see whether or not it converges or, sorry, diverges. If the limit is 0, then it could go either way. We saw that, right? We know that 1 over n diverges in a series but converges as a sequence. So we have to be careful. So only if the limit is different than 0, we can claim divergence immediately for the series. If the limit is 0 for the sequence, then series can do either or.
And you get 1/2.
K over k. Coefficients are the same.
What was
Sorry,
that?
exponents are the same, so the limit is the ratio of coefficients. If you don't like it, use L'Hopital's rule.
Okay.
I'm sorry, say that again.
Taking the limit is going to be your chapter 2 knowledge. So how do we know that the limit of this is 1/2? You have two ways of doing this. You either remember that when you have polynomials involved, if the exponents are the same, it's just the ratio of front coefficients. We have k to the first power in both numerator and denominator. And or to say, well, if I'm to plug in infinity, I get infinity over infinity. Hey, that's the L'Hopital rule, right? So take the derivatives and you get 1/2.
If the exponents are the same.
Yes. Then it's just ratio of front coefficients.
I was trying to figure out how you were doing that. You kept doing that in your, in your notes and as you were in class, and I couldn't figure out what was going on. Now I understand.
So that was first problem.
Sorry.
Plus. That was a quick draw on covering it. And the next one says summation of 1 over e to the k when it goes from 2 to infinity, which is a problem 19. Now this one, we can solve this in few different ways. The first thing I'm going to do here is try, obviously, divergence test, and it will not work. It will be inconclusive because the limit of 1 over e to the k is 0. So divergence test is inconclusive. I can solve this immediately by geometric. It takes 2 seconds to solve by geometric because your r is 1 over e. 1 over e is smaller than 1. It converges by geometric series in a flash. But the problem is requiring of us to use integral test. So let's, right? So why do this in literally one line or one step if we can write the whole page on it? That's technically how this problem is going to work out. So integral test, because we can, I guess. We are going to change the discrete function 1 over k, 1 over e to the k, into 1 over e to the x, and show 3 requirements to hold, right? We need 3 requirements to hold, which are what? Anyone remembers? Decreasing, positive, and continuous. Very good. So our function f of x equals 1 over e to the x, also known as e to the negative x, whatever you like to write, needs to fulfill 3 requirements: continuous, decreasing, and positive. Those are the 3 requirements that it has to fulfill. Well, luckily we all know how a graph looks like, so we don't have to actually do any work for this function. Graph looks like this, going through number 1. This is the standard exponential decay graph. So we see that it is continuous from 2. Let's say this is 2. So we are only considering this part, the blue part of the graph. It is clearly, where's my green? Clearly continuous, clearly decreasing, and clearly positive. This part positive sometimes gets to be confusing. Positive means all of the terms are positive, all of the y's are positive. So that means just above x-axis at all times. So visually, I see that it's always decreasing. I see that it's always above x-axis, and obviously continuous. We also know the theorem that says that exponential functions are continuous on the entire domain. We can also use that if we need to. Yes?
Do you need us to like prove these before we solve it?
You must prove it one way or another. Because if any one of these fails, the correspondence between the series and the improper integral is no longer there. Could not be there. Could not be there. So if any one of these fails, so you have to show that. Now, as I said, in this particular problem, it's very easy because we all know how graph of e to the negative x looks like. So you look at the graph and you go, oh yeah, sure, click, 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 right? Another one would be 1 over x squared. You know how those look like. You graph them and you are done immediately. The problem is when you run into a function that you don't know how it looks like and you don't have the graphing calculator. In that case, doing proofs is necessary, which are those paragraphs. A paragraph for continuity would say all exponential functions are continuous on their entire domain. Done. Continuity is proved because you invoke the theorem. Decreasing. You need to show that the first derivative is always negative on the domain you need, in this case 2 to infinity. All I need to do is to take the derivative here. Well, that's easy. It's negative e to the negative x. There's a negative in front of it, right? All of the values are negative. Derivative is negative. It's always decreasing. Awesome. Moving to the next one, right? Positive. You want to show that all of the values that you get as y's for this function is always positive. In this case, again, easy because e raised to any value is positive. Positive divided by positive is always positive. So for more complicated functions, there will be another 2 or 3 or 4 sentences in addition that you have to write, right? Because there will be multiple steps. But some form of the proof has to be there. if the function is easy and you know the graph of it, obviously it's quick and it's easy, like in this case, or those that I did in class. But I also remember I did some of those that were not, right? So I had those paragraphs. You have examples of how this is done. And once you establish these three, you can go on and make the connection between the series and the improper integral that we are about to do. Yes?
So if you put something like that on the example, and for some reason we got the answer wrong, that's still partial credit that we're getting, because you showed that the test worked, but we just messed up somewhere.
I have to answer it this way. Unfortunately, yes. So you will obviously grab to the word yes, because yeah, I'm getting partial credit, right? But you have to understand the danger of it in terms of the application. If you're trying to build a battery, or if you're trying to build any kind of energy storage, even data storage or whatever else, not being able to spot discontinuities where you are getting the infinite spikes is producing the issues in the application. So I understand that partial credit helps passing the class, but it actually deteriorates your ability to actually spot those details once you're in the workforce.
But doing that will actually help us
Yes.
figure out what we need to do to clear that up.
So now let's do the problem. We established that these three rules apply, and because of that, we are okay to compute the integral from 2 to infinity for e to the minus x dx, which we first have to rewrite as the limit b goes to infinity 2 to b e to the minus x dx, because it's improper integral of the first type. Don't forget to write this limit in every step, right? We agreed -5 per step you miss, right? Right. So integral of e to the minus x is negative e to the negative x, computed from 2 to b. Limit b goes to infinity, and we have -1 divided by e to the negative b. Minus and minus will give me plus 1 over e to the negative 2. Now, the first term goes to 0 in a limit.
Why is it negative? Yeah, negative.
Because?
I thought that's what made it 1 over, like negative 1 over.
Oh, yeah.
That's what we usually find. Why would it be?
Thank you. Is my redness gone? Not yet? I will wait here. Where's the bleach? Equals to? Well, here, 1 over e squared. Done. Now, we write the answer. Answer says, since integral 2 to infinity of e to the minus x dx converges, and the three conditions hold, the series summation of 1 over e to the k from 2 to infinity converges by integral test. This is your answer. This sentence here. That's your final 2 points in a 10-point question. Very important note here is that we don't know the value to which the series converges to. How do you know that? Oh, yes. We can find it using geometric in this case, yes. But it's not this, right? It's not that. So the integral and series converge or diverge together. If they converge together, they do not converge necessarily to the same value. So it would be wrong to say that the series converges to 1 over e to the e squared.
The series and the intervals do not necessarily converge to the same number.
Yes. So they both converge or they both diverge. That's guaranteed because those 3 conditions hold. That's what our theorem is for the integral test. Are there any other questions? Yes. Integral. INT. Clearly.
No, I have last one.
Integ test. Yes.
So I plugged in the equation I showed you, and it gives me an imaginary number as part of the answer. I mean, the
Something is off somewhere.
function they give us in the first problem looks nothing like the graph.
Yeah, you missed something somewhere along the way.
I am.
It works like a charm. I worked out that problem a few times actually because I kept losing the solution, so I know it works like a charm. You just need to spend time with it.
I have. I spent like a week working at it.
You have another 3.
Yeah, to do like.
Another 2 problems, yes.
Fun compares to mechanical engineering, well, that's
Yeah. Well. Help me much.
All right. Any other questions for this Thanksgiving Xmas review?
Can you just do a thorough and slow review of factorial concept? I'm still struggling with
Are you sure you want to be slow?
Not speedy was out. Okay.
Okay. So we have, I will start with something that you are familiar with, which is summation of n, starting at 1 to infinity, which is n plus, well, so n is equal to 1, plus 2, plus 3, plus 4, plus 5, plus, and it's going to go forever. So that's the summation of n, where we plug in n is 1, 2, 3, 4. So every time you are moving to the next term, your counter shifts by 1. There is an equivalent statement to this one, which uses a capital pi, 1 to infinity of n, which would be 1 times 2 times 3 times 4 times 5. So imagine your series that you're doing now with pi's in there. They have multiplication. They have completely different rules, obviously. Now, remember how for some summations you can put any formula here, where for pi you can put any formula there as well.
Right.
Well, this particular one is the factorial. So when I have 1 times 2 times 3 times 4 times 5 times dot 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 times, and it's finite, it ends with a value n, we call that factorial. So it's the finite. So you over here, what you have is the infinite one. But then you have the factorial is the finite, so it has to end with a value.
Question, that dot before that last n before the equal sign. That is a dot, not the multiplier.
Yeah, the three dots, this is multiplication, multiplication, and these are the three dots saying that you can have as many terms as you want.
That's what I was not, okay, this is a multiplier, then there are dot, 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 then another multiplier.
Times n, yep.
Times n. This is multiplier.
So now, what is the 7 factorial equal to? 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what the 7 factorial is. Now, looking at the 7 factorial, you can spot that, let's say, this much is 5 factorial. Let's say.
Okay.
So I can write also that 7 factorial is equal to 7 times 6 times 5 factorial. I can play these games. As long as the sequence of 5 times 4 times 3 times 2 times 1 is not ruined, I have the 5 factorial there. I can write 7 factorial as 7 times 6 times 5 times 4 times 3 factorial, because 3 factorial will have 3 times 2 times 1. So I can play these games with these numbers any way I want, as long as I'm not breaking the rule that the factorial n factorial has to have all of them from 1 to n. So 1 factorial is 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1. And 3 factorial will always be 6, and 4 factorial will always be 24, because you have to have for 4 factorial 1 times 2 is 2, times 3 is 6, times 4 is 24, and no negotiation there.
So this shorthand, the 7 factorial equals 7 times 6 times 5 factorial is shorthand.
Yes.
Okay.
Well, I might need to cancel them somewhere, just like for our ratio test,
Right.
where I need to cancel factorials, so I peel off 1. This is the reason why you can always write the two formulas that we use all the time. That n factorial is equal to n times n minus 1 factorial, and that n plus 1 factorial is equal to n plus 1 times n factorial. Observe how the one that has the factorial is always 1 less than the one that has no factorial. So n minus 1, right? Because this is a term that is 1 lower than this one. 7 factorial would be 7 times 6 factorial. That's 1 less. 6 is less 7 than 1, right? So these two formulas, we mainly use this one, n plus 1, because that's in our ratio test. And when I say you peel off one factor, you peel off that n plus 1. And now I want to put these formulas in, put examples next to them. So let's go blue. This one over here would be 7 factorial is equal to 7 times 6 factorial. This is literally what it means. Because if n is 7, replace 7 for each n, and you have your 7 minus 1 is 6. It works, right? And you see that it works because this 6 factorial will contain all of the numbers from 1 to 6, and then here's the 7. 1 through 6 times 7 is 7 factorial. So it works. N plus 1 works the same way. I can, if we want to use n to be 7, then this would be 8 factorial is equal to 8 times 7 factorial, and you see that that works as well. So if your n is 7, 7 plus 1 is 8, and then you have 8 times 7 factorial.
So that 8 corresponds to the n plus 1 factorial, right?
Yes. If so, for both of these were for n equals, let's say, 7. Now, these formulas and these ideas are very, very, very important for calculations that actually have large factorials that your calculators cannot compute. I believe that the largest factorial your calculator can display and compute. Does anyone have TI-83, 84? Yes. Yeah. I believe that the largest one it can display is 69 factorial. 70 factorial will give you error. Factorials are under stats button, and you move, I think, one to the right. There's going to be somewhere on the menu. Oh, it's under math button. So you have your second and then alpha key, and right under alpha key is a math button, and you move all the way to probability to the right. So you see it under 4 or 3 or 4. So try 70 factorial. It should, memory overflow? Yeah. And I think 69 it should show. 69 factorial it should show a number. It will be times 10 to in 10. Really? No, they were. Try 68.
I don't know if I'm typing that wrong or.
No, you just type 68 and then use the factorial. That's it.
Oh, yeah.
Oh, okay, so 69 is the factorial.
Bye.
Bye. Happy Tuesday. So what do you do? What do you do if you have to compute, let's say, 124 factorial divided by, so how would you compute that when the calculator can't go past 68 factorial? And you're supposed to calculate 128 factorial divided by, let's say, 123 factorial. The calculator won't do this. But we are better than a calculator because we can peel off 128, 127, 126, 125, 124, and what's left is 123 factorial. Yeah. And then you just multiply these 5 numbers on the calculator, you'll still get a huge number, right? But it's possible to compute. For the research that I did in number system, number theory, I computed a few factorials. I computed 121 factorial on the software. You had to write something, code and stuff. And that worked out to have, I believe, if I remember well, 3 pages formatted inch, inch, inch on a margin of numbers. 3 pages, font 12. And then when I computed 1,331 factorial, it had 27 pages of digits like that going, where few last pages, let's say the few last 7 pages are all zeros, right? Because you hit so many hundreds and so many right along the way, and that just in multiplication at 0. So it's, these values rise very quickly, and the reason why the calculators experience the overflow in memory when you go up to. So our calculators can't even go up to 100 factorial, and I hope you understand that's the reason, right? Because it will have so many numbers. Yes?
So, like, the only real world applications for this, like, with the computers, or is it like anything else?
Yeah, probability calculation, there's a lot of application for it. There's also advanced mathematics, you learn gamma functions and so on. A lot of things out there that use factorials. We only see it for our ratio test. And then you will find it in discrete mathematics, which most of the computer science students take. And you will find it also in discrete math course, so number systems and discrete math. And number theory.
I do it by accident. I was just trying to see how far I could bend without breaking it, and then it broke.
That is not accident. If you try to see how far something is gonna go before it breaks, you
Keep him busy while I go to the bathroom.
Alright, so let's do some more review now.
Yes, well, we do a problem, right? That's me keeping me busy. He's gonna ask me about the project.
Yeah, because he's really enjoying this question.
I found a different answer for this radio. Can you just take the derivative?
Yeah, we take the derivative, we do the channel, right?
Yeah, I don't know why.
So it's not a full rectangle.
Yeah, right.
But this was what? 40 over B, okay, so.
Yeah, why is that wrong?
You can, why you have B over 40? Because you went down 4? Minus 9.
This is what I got when I plugged it in. And that I solved. That I really solved the other combination. But not pick up. Yeah.
You can spend time and figure out, or you can figure out. You have this, each one for that.
No, I'm serious. That is a project. It's something that you really need to spend time and these are advanced exercises. They are not your regular homework garbage that you do for 5 minutes and then you go on and do other things. These are applied problems that actually have application, right? Applied problems. This is the stuff that you will be working on. You think hopefully working on something like this. That's the part. So you have the software, you have your calculators, you have. Have you tried tossing bone or bean sort of thing? Working? No. Try that. After Thanksgiving, you'll be gone.
Yeah.
Bring them all
I give them to my daughter.
before you get your dog. See what happens. Yes.
Go over chapter 6, like an abbreviated version of just remembering chapter 6.
Ooh, remembering chapter 6. Remembrance of chapter 6. The memory of chapter 6. Let's see. The title. Nah.
This is my drive time entertainment.
Oh my god, they all look the same.
There's a lot of language in gaming.
Chapter 6.
Oh, God. I really checked this.
In memoriam. Well, that's why they requested that, and I was supposed to say chapter 6 as soon as you walk in,
Oh, okay.
and I did.
Forgot.
No, I didn't. Chapter 6. Look at it.
What are we doing in chapter six?
Apparently, I was supposed to give overview of the entire chapter.
Okay.
All right. By the way, we're getting kicked out at 8. You know that.
Okay. Okay. This is a 20-minute summary of chapter 6.
More like 5, but that's okay. So in chapter 6, first of all, it's applied chapter. So these are applied derivatives, integrals, sorry. Applied integrals. We start with the area between two curves. Just make sure that the stream is moving. Hey, we have a viewer. Stream is moving. Hello, viewer. So we have area between two curves. So that's going to be, I know it's 6.2. I'm not going to remember all of those. So area between two curves, you have two functions that create the region between, whose integral is a to b of top minus bottom dx, and this a and b are where they intersect. And we also have, maybe in blue on the side, c to d f minus g dy version, right, when these are in terms of y. After area between two curves, we are moving to a washer method, which actually has a disk method as its special case. So we are rotating. Let's start with the disk. We have a function. We have a dx there from a to b. And the formula is pi a to b f squared x dx. That gives us the volume. Maybe I should write this area. And then washer was if you have two functions involved. F and g, still rotating on the x-axis. You have your a and b where the intersections are. And the volume is pi equals a to b f squared minus g squared in parentheses dx. So progression with a subtraction, like the area between two curves. This is area between two curves rotated around x-axis. Rotation involves the pi, right, r squared for area. And then we have shell method.
R squared for area or for volume?
R squared area times dx gives you volume.
Oh, okay.
Right, r squared area of the circle, pi r squared, right? That's why we have pi f squared.
Okay.
Now we're moving to the shell method, which cuts differently. So if I'm to draw the same function or similar function, let's say like this, and now instead of having the good old dx for rotation on y, we're going to have dy. So volume will be 2 pi c to d of y times f of y dy if the rotation is on x. And we'll have volume is equal to 2 pi a to b of x f of x dx if rotation is on y. They have to be opposites from each other. So in the methods of disk and a washer, the representative rectangle is perpendicular to the axis of rotation, and for the shell they're parallel. Just
For your A and B, is that the A and B of the X?
yes, well in this case we have A and B the way I have it. Oh sorry, this is C and D now because I'm rotating around X.
Okay.
It's A and B or C and D are always the interval in between which the dx or dy will move.
Oh, okay.
So if you visualize, in this case here, you have this representative rectangle, be literally 0 height at A, and then as it slides to the right, swipes all of the values between A and B, which is the X part, and arrives at B. And it's always perpendicular to the axis of rotation, which was X. The next one is length of the curve. So L equals integral A to B of the square root of 1 plus f prime squared dx. We also have the dy version. So we take the derivative, and this is the one that had that trick when you, if you remember. So review that. Yeah, with a half you expand and then you add 1.5 and then it condenses into the same with the opposite sign. Yeah, that's the standard one. And then we upgrade that into surface area of revolution, which is now we rotate the length of the line and we multiply it by a function to find the area of the surface of the object. So area is equal to 2 pi A to B. We have the f of x times the length of the line, which is f prime squared over x dx. And this one also had a trick, same trick, because it features the same. But also u sub is popular one because you have function in front. So it could easily be u sub. Sometimes problems for the worst formula are easier because you have extra f of x. So that helps, right? You will get there's more variety of problems to get with the surface area revolution to use u sub than for length of the curve. And we have all the physics. Yes?
I was going to say for the project, for the arc length problem, we don't have to use a wire. Like, we could use like anything. Like I could use like my lanyard. It says like put it up onto the graph and like try to.
Yes, you can. The reason why I asked for a string is because, for the wire, is because it is not going to stretch. You can use the mouse cord. You can use anything. You can, the trick is that if you use a piece of wool or something, it might stretch. Remember that you are supposed to trace it on the graph and then cut it where the graph ends from -4 to 4, I believe, which means that it's going to be depending on your scale on which you printed, right? You have to be careful about the scale on which you print, whether your 1 unit is 1 inch exactly or less than, so you'll have to, it's much easier if you use centimeters because you don't have to worry about conversion of units. But you have to make sure that whatever you are measuring with and the conversion in terms of the scale works well. And you really don't need the headache of, if you're using textile of any kind, how much it's going to stretch and mess your calculations up. So that's why I said the piece of wire, which would be old mouse cord if you have, or keyboard that is dead and is not working, or a kitchen appliance that is going to garbage, whatever.
What do you mean, like a cord wire as opposed to a piece of like?
You can do piece of wire. Yeah, you can do piece of wire.
Hanging wire.
Yeah, anything from you can find a piece of wire for like 10 cents at Home Depot, but I'm saying is you can definitely find wire some shape or form somewhere. Cannibalize the walls. Wow, that's yes. Someone shows at a house and you are hammering the drywall. There's dust everywhere. Yeah, just don't. It's not worth it. It's 5 points. All right. Was there anything else in chapter 6 that we did other than physics after this? And we had, yeah, differential equations were in. Mm-hmm.
Are we gonna have to worry about the tank like emptying? that problem. So you have like the hose going from the bottom to like the top.
Yeah, that's a really cool problem. Sure.
You think we could do one of those?
That's of course. So physics, we are talking about the force, talking about the work. Don't worry about the pressure. You're under pressure enough. What's after? Is there anything else in chapter 6 other than these concepts?
Just like the length of a bridge.
And then, yeah. After that, I remember there are exponential equations, those pre-calculus problems, 6.8 and 6.9.
Like the toothpaste one.
Ah, you remember the doormat.
The
Decay, yes.
And then there was-
And then hyperbolic functions, 6 point. So I'll just say number 7, we have the exponential / log problems, which is technically pre-calc 1. Yes, and I spelled it with K. And then we have 8 hyperbolic functions. Guys, you need hyperbolic functions for your differential equations course if you're going there. So that's it. That's your review for chapter 6 in one spot. And we did do it in 5 minutes.
Chapters are gonna have to worry about in the final. Is it gonna be one of each question or something? Or is it
No, there's no way, because we have more than 20 concepts that will be, and you know how long the problems are. So we can actually condense this, that you might have, let's say, a chapter 6 problem that involves U sub, chapter 6 problem that involves let's say it's a chapter 6, you set it up with a formula, but then you have to use by parts to solve it. And then you have chapter 6 with a U sub. And then you go into chapter 7, and it's a chapter 7 problems. Let's say you have differential equation, and you have chapter 7 partial fraction, and you have a trig sub, which will use trig integral. So kind of 2 concepts per question, and then you have a nice integration question that you say, oh, this is easy, and then you facepalm later because you realize it was a improper integral, you didn't spot it, right? Because you had a vertical asymptote somewhere in the middle.
Like test 2, yeah.
Yeah, like you think, wow, a gift question, nice. Oh, from -2 to 2, right? And then as you are unlocking the car, it's like, wait, -2 to 2, but 1 over x is discontinuous at 0. That was improper integration, diverges, and I got 7. Right? Too late. So chapters 8 and 9 are clear, right? Maybe 5 questions on series, maybe 1 on sequence, 4 on series, 2 on power series. You must have on this final exam to test integral and radius of convergence, which is what we did last class. You must have that. And then something to integrate or differentiate with power series, which is what we did last class again. About 12, between 12 and 15. The final exam, it's 2 hours, right? And no replacement question because it's a final exam. Yeah, there are no formulas given unless if it's a special physics application, right? In which case we could have a formula sheet. So there will be no formula sheet for sequences, series. All of these formulas, well, these are 6 formulas from chapter 6 that you must memorize. Chapter 7, you have to memorize the setups for partial fraction decomposition, which you've seen tonight twice. And you have to memorize from chapter 7 procedure for trig sub. So you either memorize the procedure for trig sub or you memorize the 3 formulas and cases. So either or. Also, you could memorize, if you want to, from chapter 7, the linear differential equation solution, or you can just use separation of variable and carefully do it. You will have to memorize all 10 tests for series and then one test for sequence, which is just take the limit to infinity, right? That's the only test we have for sequences. For power series, you are memorizing the Taylor series polynomial, which is series 0 to infinity of ck x to the k, or as a Taylor polynomial, nth derivative computed at a divided by n factorial times x minus a to the n. That is the formula that you must know. And there will be few things to remember from chapter 10. We only do 3 sections, so we'll take care of that next week. 1 section before and 2 sections after the exam. So we do have comfortable time, and we are also going to have at least 1 or 2 classes of the full review when we can work out more exercises. I'm glad that we had a good review tonight for upcoming exam. We did a lot of telescoping, geometric, integral tests. You guys also talked about the P-series. The only ones that we did not do, ratio root comparisons and alternating. Right? Those are the ones that we haven't done. But then we'll, yeah. Yeah, ratio and roots, they have the same, right? They have the same.
Comparison has like 2 components, right? Like is it a limit one and the
direct.
direct.
Yeah. Good. Well, okay. That's it. We'll continue this. This is, we did chapter 6, and we'll do this. Yes.
What about the after party?
Let me just after party. Yeah, now it's after party. All the people that didn't come here, that's well.